All right, we're going to get started. I welcome you to the afternoon workshop on NASA's Parker Solar Probe mission. With us today on the panel, we have Nicky Fox from NASA headquarters, Terry Kucera from the Goddard Space Flight Center, Nour Raouafi, and Andy Dreisman from Johns Hopkins University's Applied Physics Lab. And we have Pete Riley from Predictive Science, Inc. I'm going to turn this over to Nicky Fox. Sorry, I was like, who's first?
So good afternoon. I realize this is a little bit of a different format from what we usually do in that it is a workshop as opposed to a press conference. But we felt it was important to really get people together and go through some of the history and some of the real motivation for this mission. And so that when we do start getting our incredible and amazing groundbreaking science results that will be coming out shortly, that you've kind of got the lower third of your story already written. And so it is my pleasure to start telling you about NASA's Parker Solar Probe, otherwise known as the coolest, hottest mission under the sun. Parker is part of the heliophysics division. It is part of our system observatory. It has an incredibly special part for us for many, many reasons. You know, you look at this fleet chart and you see just how the heliophysics division really does embrace everything from the inner workings of our star all the way out to the edge of our heliosphere, our protective bubble here in space. And of course, as we announced on Monday, we now go even beyond that, whereas both Voyager 1 and Voyager 2 are now outside our heliopause. So we're extremely excited about the breadth of what we have. But of course, we've waited a long time for Parker Solar Probe. The mission was first thought of, first conceived, really based on a paper by a then young scientist called Dr. Eugene Parker, who published this paper and really predicted how our corona, how that hazy atmosphere that you see during a total solar eclipse, how it is continually accelerated and all the mysteries that go on in this region. He predicted that not only would it be accelerated close to the star, but it would then be continually accelerated as it moves out through the heliosphere. Of course, a few years later, his predictions were validated by instruments that were actually in the solar wind. At the time, his paper was very controversial. A lot of people didn't believe. He told me of one referee comment he had that said, you know, if you're going to publish in this type of science, you probably should go to the library first. He said all he did was solve a few equations, a few simple equations. And obviously, Gene's definition of simple equation may be different from most people's, but that's what he did. And so he predicted this. And so because of this incredible story and the fact that we also have known that the corona is more than 300 times hotter than the surface temperature of the sun, the only way that we could really go and explain why these mysteries occur is to fly a spacecraft into that region. And so we haven't sat doing nothing for 60 years. For 60 years, people have been doing mission design after mission design, trying to find out a way that we could actually achieve this incredible feat of technology. And so we were very happy that in August this year, August 12th, on a very beautiful, balmy Florida, 3:30 in the morning, we lifted off the pad in our Delta IV Heavy. Absolutely spectacular launch. We're a tiny, tiny spacecraft. We're the size of a really, really like a smart car. We're very light, but we needed to have this incredible lift power provided not only by that Delta IV Heavy, which is the largest capability launch vehicle in the NASA arsenal, but it also had an upper stage, a kick motor that then gave us further acceleration to be able to really go into the sun's corona. The important thing, of course, losing any of the influence of the Earth. We do not want to be dragged around in orbit by the Earth. We want to lose any influence from there and turn and go straight into the sun. So we were very happy with our launch. We got a perfect launch right down the center of the trajectory, which actually made some of the later early operations for us just a little bit more simple because that launch was so good. But if we want to talk about the mysteries of the corona, why are we going there? Why on earth did we wait all this time? Why are we so excited about the fact that we are now in this region? So there are mysteries in the corona. The first one, which we've known about for well over 100 years, is that the corona is 300 times hotter than the surface of the sun. No single theory has yet been able to explain why that happens. We need to go into this region to be able to sample the new plasma, the newly formed material in this region, to be able to see what processes, what physics is really taking place in there, to be able to explain to us why we see this temperature inversion, as in you walk away from a hot star and the atmosphere gets hotter, not colder, as you would expect. Another mystery, of course, is this continual acceleration of this plasma. It is moving away at supersonic speeds away from our star. It bathes all of the planets. It has impacts in different ways, but it has impacts on each one of our planets in our solar system. Of course, it also shapes our heliosphere. The protective bubble that we live in is there because of our solar wind. And then we also want to understand the very high energetic particles that we see that are associated with shocks and with transients in the solar wind. Now, a lot of people are very familiar with big storms when we talk about space weather, but these particular phenomena are occurring all the time. The solar wind never sleeps, it never stops, it is continually expanding away from our star. And so even though every now and again we do get some excitement when a sunspot actually does explode and send large amounts of material our way, we are continually buffeted and continually responding to what is coming to us in the solar wind. And so it is really, really important for us in heliophysics to understand the inner workings of our star so we can better protect life and society. So with that, it is my pleasure to introduce my esteemed colleagues on the panel. Nour Raouafi is going to come and really give you a little bit more information about why we made this daring mission, why we have to go to this region, why we couldn't do it from any other platform. Dr. Kucera is going to tell you about some of the other remote sensing, some of the other missions that we will be using in coordination with Parker Solar Probe to really use it as a fleet to unlock these mysteries. Pete Riley is going to tell you how we stitch all of these individual observations together by using big global models. And Andy Dreisman is the program manager for Parker Solar Probe. And if you have any questions about the spacecraft or the mission itself, Andy is here to answer those questions. And so with that, I will pass to Nour.
Thank you, Nicky, and good afternoon, ladies and gentlemen. As Nicky stated, can we advance? I think you should help me. So, as Nicky stated, Parker Solar Probe will revolutionize our understanding of the solar corona and the solar wind. But the question is, why do we need to go there? In other words, can we afford to live without fully understanding how the corona works? The answer is obvious, we cannot, because after all, we are living in the solar wind, which is the extension of the solar corona. And yes, we are protected by the bubble that is created by the magnetosphere, but whatever occurs in the corona will affect us in one way or another. The impact of the solar activity ranges from modest to bad to disastrous when in case of extreme events. So if we want to continue enjoying the economic, social, and technological prosperity, we have no option. We have to have a comprehensive understanding of how the corona works in order to prevent its fury when it launches these extreme events like CMEs and solar flares. There is one more thing. We have been studying the solar atmosphere for decades now. But we realize that it will be impossible to completely understand the coronal heating and the solar wind acceleration and the acceleration of energetic particles unless we send a probe to locally sample the corona and send us data to basically find the missing pieces of the coronal puzzle. Yes. So, and here where Parker Solar Probe comes. Parker Solar Probe will exactly tell us what is the source of the heating, the acceleration of both the solar wind and energetic particles. But Parker Solar Probe is not only that. It is primarily an exploration mission, and there is room for discoveries. And honestly, if you ask any scientist in the team or even outside what to expect, I think the answer would be, we don't really know. We don't know what to expect until we see the data. And we are almost certain that we will make discoveries of a new phenomenon that we know nothing about now. Now, let me tell you a little bit how things went since launch that Nicky showed us. It's pretty well from the get-go. We were put in almost a perfect orbit, and once we are in space, we start commissioning right away, and we realized that the system is behaving better than expected. And we were ahead on schedule on many things. We didn't only do that. We only gathered even data that we can use later for science, for calibration and also for science. What I'm showing here, if you go to the next one, please. So just to illustrate what I'm saying, I'm showing here an animation of the Venus flyby. The Venus flyby. This event was so crucial for us. If we don't make it, or if we don't execute it as planned, we basically don't have a mission. But once we got there, and we went by Venus, we were really surprised how well it went. Just to illustrate, I will give you two numbers. In terms of space, the Parker Solar Probe was just 300 meters away from target. Imagine that in that vast space, 350 meters is nothing. In terms of timing, we were less than a second of the time target. If this is not perfection, I don't know what is. This is, it's really good. After this, we tested all the instruments in the spacecraft, and we were preparing to get into encounter. The commissioning gave us confidence in the system. The system is working fine. It's working sometimes better than we designed it. But honestly, once we started preparing for the encounter and a few days before, you can feel nervousness in the team because we don't know what to expect in this first encounter. And we are, after all, getting so close to the sun. No spacecraft have been closer to the sun than Parker Solar Probe now. And more than that, for the whole encounter, which is 11 days, Parker has to be 100% autonomous. Whatever happens, has to solve it by itself. All we're getting from the spacecraft during this encounter, and here the movie is not to scale, we were getting what we call the beacon tones. These are limited bits of telemetry. It will tell us the overall state of the spacecraft. And we have 4 of them. They go from A to D, A for awesome. We got the first one a couple of days after we entered the encounter. We were in the mission operation room. It was cheers, high fives. It was an A. And the excitement, I don't think it lasted for long because there is a long way to go. We still have 9 days to go. But they kept coming, and they were all A's. But still, once we got out of the encounter, by the way, we got one of them after the encounter, we were not even expecting it. So the system was, as I said before, it was better than we knew it is. So we went out of the encounter. We know the spacecraft was operating normally, but we don't really know what it did exactly. We had to wait for on November 16th to get the data down and to figure out how things went. And we got the data starting on the 16th. And yes, indeed, the spacecraft was really doing well. The instrument collected a lot of science data that we started downlinking starting from last Friday. Just to tell you one thing to illustrate why I'm saying that the system behaved really well. we were expecting more than a momentum dam per day. We did just one during the whole encounter. And that's translated into many other things, good things that are fuel economy that we can use later. Now, let me go to the next chart, which basically showed what we are doing. What is the science, what you're looking for? This just illustrated pieces of data from the 4 instruments that are in the spacecraft, and they will basically teach us about the 3 phenomena that Nicky mentioned earlier, but they will tell us way, way more than that. And by the way, all this data was recorded during the commissioning from fields. For example, we can see a type 3 burst, sweep, we see the solar wind, ACES, we see the energetic particles, and from WSPR, we see the Milky Way. That is, by the way, the first image we ever recorded by WSPR when it opened its door. Now, as I said, this is the commissioning data, and I'm not going to leave you there. We'll go to the next one, which is the first image you will ever see from WSPR from the encounter. This was recorded at about 40 solar radii from the sun, when the spacecraft was 40 solar radii from the sun. And what we see there is a streamer. If you look at the equivalent from other spacecrafts, basically you see a full bright structure here. But here we are seeing the fine structure of the streamer. You see multiple rays here in the streamer. And probably there is also something going on here. Probably it's the initial stage of very small CME. By the way, this is Jupiter, and the dark dots are just negative Jupiter because of the image correction. Now I will turn it to Terry Kucera to tell us about the role of the other assets and supporting Parker Solar Probe.
So Parker will be supported by numerous other space missions and observatories. As Nicky said, we have a fleet of spacecraft observing the heliosphere, the sun, the solar wind, and how it affects the solar system. And we're just going to show some examples of that. This is an image of the sun in extreme ultraviolet light by the Solar Dynamics Observatory in Earth orbit. And it's showing what a tremendously complex and dynamic area this corona is, and this is what's driving the region that Parker is flying through. So we need to understand this to get important context for understanding the Parker observations. And this is sort of the base area where things like coronal heating, acceleration of a solar wind, and solar activity are coming from. And again, those are key science goals for Parker. So next. Okay. This is a diagram of the solar system from above, showing the location of Parker during the first perihelion pass just a month ago. Here's the Earth. We have a number of spacecraft around the Earth right now, near the Earth. Here's the location of the Stereo A spacecraft. Both Stereo A and SOHO, which is near the Earth, have coronagraph instruments that were observing the actual region through which Parker was flying. Also, another point of interest on this plot is if you see these sort of faint spiral lines, those are our first approximation of what the interplanetary magnetic field is shaped like. And that's known as the Parker spiral, after the same Gene Parker that Parker Solar Probe was named after. And he was the first one to predict that we would have these spiraling field lines as a result of the sun's rotation. Next. Okay, so here's some actual data from the Stereo A spacecraft. I'm on the Stereo team, and we actually did a special observing campaign to support the perihelion pass. So this is actual data from that. You're seeing data from 3 different telescopes shown in 3 different colors. And the white dot is not Parker. We cannot actually see Parker. We're not that good. But it's where Parker is in our field of view, and it's actually passing behind the sun. But we are going to be working with this data, and we will be able to give really important context for what Parker's flying through, all the variations in the solar wind, and putting that together with the SOHO data to get a 3-dimensional feeling for what's going on in that portion of the corona. And conversely, not quite yet, but we at Stereo will be very excited to have Parker data from a region that we've been studying for some time, but we haven't actually been able to reach out and touch. Parker's going to be giving us ground truth measurements in this region, we've only been able to observe from afar. Okay, so I've been talking about imaging, but also there are a number of spacecraft around our solar system that are making measurements, or what we call in situ measurements, measurements at the spacecraft. And of course, Parker's doing that. And there's similar instruments in other spacecraft around the solar system. And that's important because the solar system is a big place. And these events that we're looking are also very large. And what we're, in many cases, I mean, they vary in scale. But this is a data-based model of a number of coronal mass ejections that happened a few years ago. And you see they're expanding out into the solar system. We were able to observe these with a number of spacecraft in different parts of the solar system, sampling the characteristics of a solar wind, magnetic field, energetic particles as they went by various locations. But we had nothing really close into the sun, and now we do, and that's going to be very important to round out our understanding of what's going on with these, how they change as they go out, and to test our models. And Pete's going to be talking more about that.
Thanks, Terry. So global models of the corona and the inner heliosphere are important for any space mission, but that's particularly true for Parker Solar Probe because of its unique instrumentation and its unique trajectory. So what I'm going to do is illustrate with 3 examples of how we think that the models can contribute to our understanding of the primary scientific objectives. So the first one is going to be that the models can help us to refute or support particular theories of the physical processes that are going on in the solar corona. The second one is that we'll be able to map the measurements that the spacecraft makes back to their solar surface at 1 solar radius. And then the third one is that they're going to provide a global context for understanding these observations. Although they're presented often in a nice, simple way, they're very, very complicated observations, and they take quite a bit of focus to be able to understand what they're telling us. So, as Nicky and Nour both mentioned, one of the primary objectives of the mission is to understand what heats the corona and what accelerates the solar wind. And models can help us understand this because they have some of those theories built into them. So if the model does better with a particular idea embedded, then that tends to support the idea. If it does worse, then that might mean that we might need to look for a better idea. So one of the models that we've developed does include a model for self-consistently heating the corona and accelerating the solar wind. We don't have any Parker data at the moment, so I can't compare it and tell you whether or not it has improved the model with that kind of comparison. But what I can show you is a study that we did on the Great American Eclipse from 2017. This was our most detailed simulation and prediction of the structure of the corona, which we did a week before it was actually observed. And we incorporated, in fact, one of the major improvements was incorporate this idea for how the corona is heated. So what you can see here is on the upper 2, top left and middle panel, are 2 photographs that were taken in Oregon. And then in the column on the right, you can see simulation results. Now, beauty is in the eye of the beholder, so I'll leave it up to you to decide whether or not that's a good comparison or not. I personally think it's absolutely fantastic, and it tells us what the underlying structure is. So we can look at the magnetic field, and we can see how that field is composed to actually create the structure that we see. So for us, that was a very, very positive result, and it allows us to have more confidence in the model itself. And when we start looking at the Parker data, I think that we're going to be constrained even more, and it's going to help us to advance the theory even more. Could I get the next view graph? So the second illustration in terms of the modeling is that we can model all the way from the surface of the sun, where we observe the photospheric field, all the way out to 1 AU. And we can fly the Parker spacecraft through that, and we can sample all of the plasma and magnetic field variables in there, and we can also look at each field line and trace that all the way back to the surface of the sun. So in principle, we can tell you where on the sun a particular parcel of plasma that was measured by the Parker Solar Probe actually came from. And this is an attempt to do this. This is a simulation that we did 1 week before the first perihelion encounter, and you can see that prior to the first encounter, so prior to the beginning of November, we were immersed in an equatorial coronal hole with a positive polarity. But even before we hit the first encounter, we became embedded in a second equatorial coronal hole with a negative polarity. So based on this, our prediction would be that the fields instrument is going to see exclusively negative polarity field for the entire duration of this first perihelion pass. So I'm particularly excited to know whether or not that turns out to be the case. And if it's not, I'm not too concerned, because that means that there's something missing in the model, so that will allow us to help improve the model itself. And then the final illustration was that we can provide a global context for interpreting both the in situ measurements as well as the remote solar observations that the WSPA instrument is making. This is actually the original movie. This is not the replace movie. Okay, that's fine. I'll stick with this one. Okay, so what you can see here with the two triangles, those are the fields of view for the WSPA instrument. Okay, so this is actually before the instrument's turned on. The instruments won't turn on until we get much closer. And you can see the trajectory of the Parker probe as it spirals in towards the sun. What I'm personally really excited about is that you can see that the co-rotating structure that Terry mentioned is sweeping over at that Parker spiral. However, as it moves in towards the sun, it begins to accelerate, and it's accelerating both towards the sun and around the sun. And because of that, there's this unique effect that's almost like a stretching of time that we've never seen before with a spacecraft. So you'll see as it actually comes in and accelerates, it's going to sit on one parcel of plasma, a piece of slow plasma, and it's going to hang there for about 2 or 3 days. And one of the consequences, if it works out, so you can see now it stays on that green, and then as it comes back around again, it's going to get swept up by the faster wind that's behind it. So we've always had this trouble trying to understand the relationship between temporal and spatial variations in the solar wind, and this, I think, is a really exciting opportunity for us to finally deconvolve that. So I'm really excited about what the solar probe is going to reveal to us, and hopefully how it's going to help us improve the models. And eventually, these are research models, but eventually the knowledge that we gain will allow us to transition these into space weather forecasting tools. Okay.
We're good? Okay. We'll open the room to questions from reporters. Do we have any questions?
Harvey Lyford, freelance. If no one has a relevant question, I'd like to ask one that goes back to the Voyager briefing a couple of days ago.
Okay.
We've been having a couple of a discussion about the bubble, the heliosphere itself, and then we were told at that session that there is the Voyagers are now at a new bubble, 100,000 times larger. The question is, are these bubbles abutting each other, or are they like Matryoshka dolls? The heliosphere is within the other bubble.
Wow, that's a really interesting question that I'm not qualified to answer. But it is moving into another large bubble. There are different theories as to exactly how those bubbles are formed, whether or not at the edge of ours is a smooth edge, whether or not it has little bubbles and little pockets in it, exactly whether that is yet another bubble, whether they're nested bubbles. I think the belief is it is kind of another bubble that abuts it. You know, our star governs our place in the Milky Way as we orbit around in our galaxy. That is kind of the next large bubble outside. What is causing that bubble? You'd need a dedicated mission to go outside our heliosphere and start really looking at that in great detail to give you a really good answer. But one of the main things is it's kind of you know, our star is inside yet another large bubble.
And our heliosphere, obviously.
Yes.
Thank you.
Do you have any other questions from reporters in the room?
There is one in the back.
But you have good eyesight.
Hmm?
You have good eyesight. Didn't use the model. All our models.
Hi, thanks. Yeah, Jonathan Amos, BBC. Could you just talk a little bit more about that WSPA image that was taken at Perihelion? What day was that, and the exact distance from the sun as well, and what we see. I wasn't quite sure about the remark you were making about the repetition of Jupiter's in the image. It's an artifact, clearly.
Okay. So yes, I think the first, it was a little hard to hear, but the first one I think was some details about perihelion. So that was on November 5th, and that was our first closest approach. We will use, so Nour talked about flying past Venus and how important that was for us to kind of turn the spacecraft and get it going into the sun directly. We will use another 6 flybys of the planet, and that will gradually then kind of step our closest approach closer and closer with each of those perihelion passes. And there are a number of passes at each of the different stages, and that allows us to actually do different types of science. One of the really nice things that Pete illustrated with that, with that last movie was our ability to sit in a certain pocket of plasma and stay in there for a number of days, and that, sort of changes how the spacecraft moves with respect to the solar wind, changes with each of those different perihelion passes. And so we're not just looking forward to our closest approach, if you like, when we're below 4 million miles from the sun. We're already excited about what we're doing even now, and each one of those Venus flybys will give us kind of a different look and a different feel and a different type of science that we're doing. Do you want to add?
Well, I'll add one thing. I think during the development of the mission, we stressed so much that the 10 solar radii that we are going below. But from this first orbit, we are at 35 solar radii. And we are the closest ever to a star. The spacecraft that was closest before solar probe is Helios, was at 70 solar radii. We are half that distance. This is so close to the sun. It doesn't really, what we are looking at now is completely brand new. Nobody looked at this before. And we just have to wait for the data and see what we are seeing. And at least from the very first bits of the data, it looks very exciting.
And I think the second part of your question was about the negative Jupiters. And so that is, we take a number of images and then sort of stack them up to be able to do the image processing. The spacecraft is moving so fast that Jupiter is moving in the frame of the photograph. And so, it's like trying to take a picture as you're driving along in the car and you snap like 7 shots and you see different parts of what you're traveling past. So even Whisper is doing a great job of imaging the corona. The spacecraft itself, so the platform that the camera is sitting on, is moving so fast that Jupiter appears in different locations. And so when they do the image processing, you see one image where you see a bright location of Jupiter, and that's exactly where it was, I think probably in the middle of the sequence. Yeah. And then the others are just, they've been removed because of the image processing.
Hi, Sid Perkins, freelance. I have a question about, again, we've always heard that the surface of the sun is 10,000 degrees or so, and the corona is millions. Are you getting close enough to the sun to be able to get into an area that's actually cooler than the atmosphere, or is your closest approach still going to be in a very hot part of the corona? Is maybe getting a better mapping of that temperature profile part of this mission? Can you expand on that a little?
So at our closest approach, we are well in the region of 3 million plus degrees plasma. Of course, we are out around Venus, and then we're flying all the way in, and so we actually see a lot of temperature gradients. I think what you're asking is, are we going to get close enough to the surface to see the other side of the gradient? And no, that would be way too close. And that would require probably another 60 years technology development to be able to go that close to the star. Because most of the heating that we have to deal with, most of the temperature, that we have to deal with on the front side of our heat shield is because of the photons from the sun. It's not actually from the 3 million degree plasma, because the plasma is very tenuous. And so the closer you get to the sun, even though you may be in cooler plasma, you've got a lot more photons coming to you. So the actual temperature that you would have to deal with is kind of irrespective of the plasma. Andy, did you want to add anything?
No, I think that, I think that answers that well, thank you.
Okay.
Do we have any questions from the chat?
Yes, we have a question from Lisa Grossman of Science News, or we have two. The first question is, why did they start downlinking the science data on December 7th if they could download the data on November 16th?
Actually, so that was a good question. Why did we have to wait till December? And that really is to be able to close the link and to be able to get down even though we knew we were good and we had our beacon tones and we could start seeing some data on the 16th, we're still very far away, and so we can only bring down data at a very low rate. And so we bring down, obviously, all the health and safety data, all the spacecraft data, make sure that everything is working fine. The science data, it was as quickly as we could physically bring it down. But the closer to the Earth we get, the easier it is to close the link and the more data we can get down.
One of the other constraints we have, so the spacecraft is protected by the thermal protection system. You can think of it as an umbrella on a hot, sunny day. It keeps the spacecraft behind it in the cool shade. And we always have to fly with that thermal protection system aimed at the sun. There is a high-gain antenna on the spacecraft that has a motion that's able to track the Earth, but at points in the orbit, the thermal protection system interferes with the antenna's ability to communicate. So prior to December 7th, we couldn't point the high-gain antenna at the Earth because the thermal protection system had to remain pointed at the sun. After December 7th, the high-gain antenna could point, and then sometime at the end of next week, we lose that ability to point as well as the Earth goes behind the sun. So it's just, we're geometrically constrained.
For this particular orbit.
For this particular orbit.
But we have many orbits where we can downlink the science data almost immediately.
Orbit 2 is a great orbit.
Yes.
3 as well.
Yeah, we'll bring down a lot of data on orbit 2.
And that's one of the reasons that we carry enough storage to be able to hold at least 2 orbits worth to allow us to be able to not lose data. Sometimes we have to go into an encounter still with data from the last encounter on the recorder, but that's not a problem. Everything comes down the next one.
The next question is, the spacecraft broke a speed record, right? How fast was it going, and how fast was the previous fastest spacecraft?
The actual record of Parker Solar Probe is 234,000 miles per hour, and Helios is way, way below that. I don't remember the number exactly.
It's roughly half.
It's half, yeah.
But that isn't our top speed. That was just the top speed that we achieved on this orbit.
On this orbit, yes.
Harvey Lyford, freelance again. This time it's about this message. We only saw a little cartoon showing part of the orbit for about 11 days, and I'm not really clear on what the orbit is and how many times it will pass the sun.
Sure.
And how many times it's near Venus and so on.
Sure. So if you think of the orbit as if the sun in the center, and you think about doing the petals of a flower, and so you're going to go very close to the sun on one side, and then you come out around the orbit of Venus on the other. And so as it moves around, it's going to sort of cover all different areas as it does these petal loops. Of these petal loops, there are 7 of them that involve us flying past Venus. We are always at our aphelion or our furthest away point. We are always around the orbit of Venus. That is the kind of location of our furthest away point. And then our closest point is well in the corona. And so of those, there will be 24 orbits, so we'll do 24 petals in our prime mission. And then of those, 7 of them were perfectly aligned with Venus to be able to do the flybys. Clearly, our launch was planned to coincide with Venus. As Nour said, that was the really critical thing, was to be able to make that first Venus flyby. So our whole launch window was predicated on the question, why did you launch at night when you're going to the sun? The whole the launch was predicated on where Venus was, and then we have another 6 occurrences where we can fly past Venus, and each time we fly past Venus, we trim or we kind of shrink that petal so it's closer to the sun at the perihelion.
It's a nice illustration on the Parker Solar Probe website. If you look
Yes.
at where is Parker Solar Probe, there's a very nice image of the 24 orbits.
Mm-hmm.
I have questions from our reporters in the audience. Any final questions from Chad?
We have a question from Leah Crane of New Scientist. When can we expect preliminary results from the first orbit to be released?
The data?
Well, preliminary results.
From this KA period that we are downlinking the data, we'll get about a fifth of the data, all the data that we collect during this encounter. It will take us more time to get all the data down, but whatever we got, we are looking at it, and as soon as we get results, we'll get them out.
So the science teams are obviously
Yes.
working. I think we started downlinking data sometime on the 7th, and certainly between the hours of 2 and 3 in the morning, I got a lot of texts from PIs that were seeing their data for the first time with a lot of excitement of, good, just really good things. There will be some data plots shown even at this meeting. I think there's a session tomorrow afternoon and one on Friday morning where they will show some preliminary data, but there obviously won't be any results because they've only just got the data. But, if you'd like to see a magnetic field profile of a flyby through the corona, go see Stuart Bale's talk on Friday morning, for example. There will be some preliminary data shown, but the results will take a while. As both Nour and Andy noted, we have to wait till the end of the second orbit, or the second encounter, to be able to get all of the data down, and it takes a while. It's a mind-blowing mission. As Nour said, if you ask everybody, what were you expecting, they're going to go, I really don't know. The other thing is we're moving at roughly half the speed of the solar wind, and so on the way in, we're kind of crashing into the solar wind as it's speeding out towards us. On the way out, we're moving in the same direction, which means that features look very different on the way in and on the way out, and that takes a while to sort of unpack those details to be able to really produce results. But I am excited that we will have results, really great results next year.
Thank you.
Any last questions? Thank you to our panelists. That will close our session.
Thank you.
Very nice.